So we're going to finish up chapter 17, do some problems at the end of the chapter. Don't know if we'll do all the problems today. We'll do some of them tomorrow. But try to look over the old tests, and we'll have an opportunity tomorrow to work some of the problems on the tests. So the thing that we're talking about are titrations. And titrations are where we're adding their neutralization titrations. So fundamentals of all neutralization titrations is that you're adding an acid and base together, and those two things are going to react with one another. So this is an example problem of something that you may see. The thing I'll tell you is that we're going to do a bunch of different combinations. The problem I'm going to give you is it'll be a pair of one. So it may be a certain volume of HCl, and the key on this is to recognize what is HCl. So we need to recognize that HCl is a strong acid. And then it's being reacted with a certain volume of NaOH, and NaOH is a strong base. So this is a titration of a strong acid and a strong base. So we want to recognize that. And the problem that you'll do, where this one we're going to work 5 different volumes added of the strong base, will be one combination. Okay, so I'm not going to ask you to do all 5 in a problem, because you'll see this would be lengthy time-wise. Okay, so the way that you approach something like this is recognize that a strong acid is simply represents H+, a strong base is OH-. Those two things are going to react to form water and a neutral salt. In this case, the neutral salt, if you take the counterion from the chlorine, then the counterion of the hydroxide would be sodium chloride. Doesn't matter what it is. So the way that you approach these titration problems is find out how many moles of each reactant that you have, let them react, and find out what's left over, or what products are formed. So if I take concentration times volume for the HCl, so 25 milliliters times 0.1, that's 2.5 millimoles. Remember, moles equal concentration times volume. And it's in milliliters, so the answer is going to be millimoles instead of moles. And if I do the same for the sodium hydroxide, start with the 5 milliliters first. It'd be 5 milliliters times 0.1. It would be 0.5 millimoles. So the limiting reagent now is going to be the hydroxide. So I'm going to lose 0.5 millimoles of the hydroxide. I'm going to form 0.5 millimoles of both the salt and water. I'm going to lose 0.5 of the H+ millimoles. So if we think of our ice initial change and what I have left at equilibrium, I've consumed all of the OH-. There's none left. It's gone. I've got 2 millimoles of the H+ left. I've made half a millimole each of water and salt. So the thing that's going to control pH at this point is going to be the H+ that's in excess. So the pH at that point, and that's what our goal is, to calculate the pH at this point, is just going to be the amount of strong acid that's left over. It's the concentration of the H+ as the definition of pH. So it would be a negative log of the concentration. I know how many millimoles I have. I've got 2 millimoles. And my volume is I started with 25 milliliters, and I've added 5 milliliters. So the total is 30 milliliters. Millis cancel out. That's moles per liter, so that's molar. So that's the units I'm looking for. So I'm just going to plug that in. So 2 divided by 30, negative log. And this initial pH, or the initial pair, is pH of 1.18. All right, question on that? So I let the two things react, found out how much of each reactant I had, allowed the two things react, and then I found out what was left at the end. And then I find out, do I have excess strong acid? Do I have excess strong base? If there's none left, I look at my products. My products are going to control what pH are. Okay. All right, I'm going to copy part of this, and if I can figure out how to use my copy tool. All right, I just want to get the top line up here. Start with that. I think I already got that. I can do that anyway. I'll try to copy that. If I go to the next page, yeah, I already got it written down. Okay. Now we're going to do the one with 10 milliliters. There. So if I start with 10 milliliters, I'm going to do the same thing. I'm going to set up my ice. And if it were a 10 milliliter volume added this time, there's still the exact amount of H+. There's 2.5 millimoles. If I take my 10 milliliters times 0.1, now there's 1 millimole of the OH minus. So when the two things react, still the OH minus is going to be the limiting reagent. So I'm going to consume all of that. I've got 1.5 left of the H+, 0. I formed 1.5 of water, plus 1.5 of the neutral salt. So the things that are contributing to pH at the end now are the water, the neutral salt, and this excess strong acid. The excess strong acid is the thing that's going to control pH. So similar to what we did in the last one, pH is the negative log of the concentration of the H+. The concentration is equal to the moles divided by the volume. So I've got 1.5 millimoles. This time the total volume is the initial 25 plus 10, so it's 35 milliliters. The millis cancel out, that's moles per liter. So 1.5 divided by 35, take the negative log. I'm expecting the pH to be going up slightly. Now it's went up to 1.37.
How did you get to 37 or 35%?
The 25 milliliters initially, plus the 10 I've added. It's just the total volume. Okay, other questions on that one? All right, let's do it again. So, if I can remember how to paste here. Do this where this came from. Nope. Okay. We're going to do it 20. So now 20 milliliters added. H plus OH minus yields water and the neutral salt falling through ice. So it's still the 2.5 initially, 25 times 0.1. But now if I take 20 times 0.1, it's 2 millimoles of OH minus. There's none of these initially. So still it's the limiting. So minus 2, plus 2, plus 2. So at equilibrium, I've got 2 moles of water, millimoles of water, 2 millimoles of the neutral salt. I don't have any OH minus, and I'm down to 0.5 millimoles of the H plus. Again, the H plus is going to control the pH. pH is going to be equal to the negative log of the moles. So the 0.5 moles of the H plus. Now the total volume is the 25 initial plus the 20. I'm up to 45 milliliters. Total volume. Millis cancel out. 0.5 divided by 45. Take the negative log. pH is all the way up to 1.95. So we're going to do the last two. Right, so now at 25 mil volume added. So at 25 mils, still the initial amount of H plus. If I go concentration times volume for the OH minus, now it is also 2.5. So initially, there's no products. So the two things react and annihilate each other out. There's none of the H plus left. It's been completely consumed by the OH minus. So what I'm left with is just the product. And the products are water and this neutral salt, NaCl. All right, so what's the pH of this guy? There's no excess H plus, there's no excess OH minus. If I've got a mixture of water and HCl, what's pH? Or water and NaCl? Neutral pH, yeah. It's a neutral salt, so the neutral salt doesn't contribute to pH. You just got water. So this would be the equivalence point, pH 7. So the key to this problem, if you've got conditions where these two things have canceled each other out or consumed each other, that's the definition of the equivalence point. Okay? And for a strong acid, strong base, titration, strong acid, strong base, the equivalence point is at pH equal to 7. So if I can recognize that I'm here in the titration or the mixture of these two things, I know it's pH 7. Now the key thing is recognizing that it truly is a strong acid, strong base. If it's a strong acid, weak base, it's not 7. And we're going to cover that in a minute. But this is true of strong acid, strong bases. Okay, we got one left to do. Let's do with the 30 mils. So we're going to 10 colors of black again. So with the 30 mils of it, we've got our H plus and our OH minus, the old water and the neutral salt. We have 25 mils of 0.1 molar HCl, and now we're doing 30 mils of 0.1 molar NaOH added. Right, my concentration times volume to find the number of moles. The amount of HCl stays the same in all of these. It's 25 mils of HCl in all the problems, so 2.5. Concentration times volume for the NaOH gives me 3 millimoles. Initially none of the water and HCl. So this time what's in excess is the OH minus. So all the H plus is consumed. So I lose all 2.5 millimoles of the H plus. I lose 2.5 millimoles of the OH minus. I form 2.5 millimoles of water, and I form 2.5 millimoles of the neutral salt. So there's no H plus left. There's 0.5 millimoles of the OH minus left. There's 2.5 millimoles of water and 2.5 millimoles of the neutral salt. So what's going to dictate pH is the thing in excess. In this case, it's excess OH minus. So the way that we deal with this one is we calculate POH first. So POH is equal to the negative log of the concentration of the OH minus. So it's the negative log of the number of moles divided by the total volume. So we started with 25, we've added 30 to it, so the total volume is 55 milliliters. Milli and milli cancel out, so that's molar. So I'll take 0.5 divided by 55, take the negative log, and it's 2.04. Now that's POH. If I want pH, I take 14 minus the OH. And the pH has jumped all the way up to 11.96. So if I think about the progression, we were pH 1, pH 1, pH 1. Even at 20 mils, we were still in the pH 1 range. And then pH 25 mils, we got to pH 7. And the next 5 mils, went all the way up to pH 12. So this is kind of what we talked about in class yesterday. It stays low, stays low, stays low, and then pH jumps up sharply and then levels back off. Okay? Where the 7 was the point where the equivalence point, the middle of the titration curve. And this is a plot of volume of the titrant, which was the OH minus in this case, versus pH.
Where did you get the?
Okay? It's the 25 milliliters initially, plus the 30, the last volume we added. Okay. What else on that?
Okay, can you explain how which one is excess?
Right, so the way that you determine which one's in excess is always go to the last line. At equilibrium, what's left over? One of the compounds is going to be consumed, or both of them are going to be consumed. But if there's anything left, that's the compound in excess. Right. Okay. So here's some questions about that would apply to this, and these are a couple of old exam questions I plucked out and put in here. It says, when titrating a monoprotic strong acid versus KOH, and we need to recognize that KOH is a strong base. So this is a strong acid being combined with a strong base. It says the pH will be less than 7 equivalence point, pH will be greater than 7 equivalence point, pH would be equal to 7 equivalence point. Want to make that a clicker question? What do you think? Say again? C, yeah. So once we recognize this is a strong acid, strong base, like I talked about on a couple of slides ago, you recognize that, that's always going to apply. So absolutely, it'd be choice C. Okay, so let's look at the other example. It says you've got 0.1 mils of HClO4 and saturated with 0.27 molar lithium hydroxide. What's the pH of the solution when you've added 50 milliliters of the lithium hydroxide? So there's 50 mils of this. So again, recognition of what things are. This is perchloric acid, it's a strong acid. This is lithium hydroxide, it's a strong base. So in this reaction, what's occurring, and I'm going to write above it so I have room, is this is a strong acid, strong base titration. It's going to form water and a neutral salt. So I need to find out what are the moles of each one of the compounds. Okay, so concentration times volume. So I've got 0.8 molar times 100. So what is that? 18 millimoles of H plus. I've got 50 milliliters times 0.27, 13.5 millimoles. Okay, so let's just look at that and see if we can figure out what the answer would be. Do I know what's going to be in excess? The H plus, right? So I formed 13.5 of water. I formed 13.5 of the neutral salt, but they don't really matter. Right? I don't have any OH minus left, and if I subtract that, I've got 4.5 millimoles I'm doing that right in my head. Okay, so there's excess OH minus in this. So this is the thing in excess. So if I look at this, what are the possible answers if you have excess H plus? So I've got excess H plus. Are all of these possible answers? Which one's not a possible answer? Okay, very good. So by process of elimination, I can eliminate that one. Now sometimes when you do a standardized exam, there's only going to be one logical choice. You don't have to do the calculations. On this one you do. But I want you to understand that process, that when we write these exams, a lot of times we'll give you, if you understand the problem, you can find the answer without even doing the calculation. Okay, there's only going to be one logical choice that's there. So if we've got excess strong acids. So it's the negative log times the concentration. So it's the negative log of the 4.5 millimoles. What's our total volume now? Okay, we started with 100, we added 50. The millis cancel out. So 4.5 divided by 150. Take the negative log. And I got 1.52. Okay, question on that one. Again, it's just the thing I want to emphasize. You got to know what the strong acids and strong bases are. Recognizing this portion of it. If you don't know that, you don't know how to work the problem. Okay, that's the big start. Okay, so here's yours. Do it on your own. Dang, that's fairly close to what we just did. Give you a couple minutes. And emphasis this. You figure out the answer, you put it in. We'll talk about it in a second. I want to know your answer here. Like your strategy, some blueberries offset the milkshake.
But that's on not you. Yeah, that's another good.
I like my Diet Coke and double meat cheeseburger. All right, got 11 answers. A couple more. Okay, we're going to talk about it in a second. Hang on. See if we get your answers in. Two more. There we go. So, all right. So a little stair stepping, but C is the predominant answer. Now you can talk about it. So you discuss it amongst yourself and see if you think C's right. Because a third of you thought it was C.
Yes, yeah. Okay. 2 seconds. Okay. I mean, I thought it was because it was supposed to. No. I forgot to put it on it.
Okay, give an answer.
I got down to. This is pretty complicated. No. I know.
Okay.
I'm just.
Got more answers.
I didn't even.
One more. We had 19 last time, we need 19 now. There we go. Okay. So almost everybody went with choice C. Had one person that said y'all are wrong. Okay. So I've kind of started the math. We've got excess OH minus. There's 9 millimoles of that. So with that, POH is found by the negative log of the concentration of the OH minus. So it's going to be the negative log of the 9 millimoles divided by the total volume. In this case, we started with 100. We added 100. So it's 200 milliliters total. So 9 divided by 200 is 0.045. Negative log gives us a POH of 1.35. And subtract from 14, and you get pH of exactly 12.65. Okay, I had a typo in my problem, obviously. So I'm not going to grade that for that reason. Numbers didn't match. Okay. In a case like that, choose the closest, which is almost what everybody did. But yeah, that's a typo on my part. All right, so let me go in here in my notes. Don't grade.
So are you gonna not grade this one or the other one?
Both.
Okay. I was making sure.
I mean, both of them. Neither of them have a right answer.
Okay.
So I'll reject them. And I gotta go fix it. Okay. So we've got an idea of how we deal with strong acid, strong base titrations. Now let's talk about the other possibilities. So one of the other possibilities are the combinations of the weaks. And I'll be honest, a weak titration, a weak acid with a weak base is really tough to do. Okay, because it's partial ionizations. What we can deal with, though, is a weak acid in combination with a strong base. Or the converse of that, what we're going to talk next, is a weak base with a strong acid. So what happens when we titrate a weak acid with a strong base? We remove some of the weak acid is converted into the conjugate base. We can determine the initial pH by just treating it with just a weak acid. In the region where there's excess acid, what's happened is I've taken some of this weak acid, and during the course of the titration, HA, and I've converted it into its conjugate base as it reacts with the OH minus. what is it when you have a solution of a weak acid and its conjugate base? What does that make? It's a buffer. Okay, so we treat it as a buffer. So once you go start the titration, we have to find out how much weak acid's left, how much conjugate base is formed, and then we go into the H and H equation, or the buffer equation, calculate pH. At the equivalence point, I'm left with just a weak acid, so all of the HA has been converted into the A minus. So I find out what is the concentration of this weak base and treat it with the simplified quadratic for a weak base. OH minus is equal to square root of KBCD. KBCD. All right. And that's what pH is going to be at the equivalence point. And this is not going to be pH 7. So pH is not equal to 7. It's something different. It's going to be higher than 7. And then after the equivalence point, now I've got excess strong base. So just find out how much of the strong base is there and use POH from that to calculate pH. These are a little trickier, but we've talked about all the chemistry on how to deal with them. So if you think about it in the course of looking at the curve, if you start with just the weak acid, you treat it initially as a weak acid. We talked about how to do that in the last chapter. In the region where I'm titrating the weak acid with a strong base, it's making a buffer. So this region in the middle is what we think of as the buffer range. At the equivalence point, all of the weak acid has been converted into the conjugate base. So we treat that as just a weak base. We did that in the last chapter. And then beyond the equivalence point, there's just an excess OH minus, and that's just like the previous problems we did. Okay, so let's see if we've got a problem like this to look at. Well, this is going over all those steps that I just talked about. So initially, it's a weak acid. At the before the equivalence point, we calculate how many moles of the HA is left, how many moles of the A minus have been formed, and then we plug that into the Henderson-Hasselbalch equation with the pKa. Now, one thing about this titration is that halfway through the titration, there's some information that's valuable for us to see. So if I'm starting with HA, and I'm forming A minus, and let's say that it takes 100 milliliters of the OH minus to accomplish this. So we're titrating it with a strong base, OH minus. And it takes 100 milliliters to the equivalence point. So that's where I've converted all of the HA into A minus. So if I go halfway, this half equivalence point, halfway through the titration at 50 milliliters, and if I did the calculation, let's say I started out with 1 mole of this, and I'm going to end up with 1 mole of this at the end, but halfway through, if I add 0.5 moles, that means there would be 0.5 of this left, there would be 0.5 of this formed. All right, so there's equal moles of the HA and the A minus. So do you remember anything about the buffer equation when we had equal moles from yesterday?
It's just pKa.
Because the log of that ratio, this is 1, log of 1, 0, 0. pH becomes pKa. So at halfway through the titration curve, pH is equal to pKa. So once I recognize what type of titration this is, we can look at this and go halfway. So it's 25 mils to the equivalence point. The half equivalence point is 12.5. I know this particular system has a pKa of 3.8, 3.9. Okay, so I can actually learn something about the Ka of my weak acid in this system. That's one of the ways that we calculate it, is doing a titration curve. Okay, so if we're titrating, going beyond, so if we look at the equivalence point, what's happening at the equivalence point is all of the HA has been converted into the conjugate base. So now what I do is I find out the moles of that I have. So all of this HA has been converted into the A minus, take into account the total volume to find out its concentration, and we treat it just like a weak base that we talked about in the previous chapter. So a weak base, OH minus, equals the square root of KB CB, where this is where you're finding what CB is in the system. And then beyond that, all I do is find out how much of the OH minus is left hanging around and plug that into the expression for POH. Okay, let's see if what we have. So when we monitor titrations, and we're going to work these type of example problems. I've got a couple of these in the end of chapter problems we're going to work, so not skipping those. We're going to do some in a minute. One of the ways that we monitor the titration is use a probe that lets us see that directly, and that's the pH meter approach. Sometimes you don't have a pH meter available, so there's an alternative way that we can do it, and we can use an indicator that changes color to tell us when we've reached the end of the titration. And that doesn't tell us our progress in between. So if we think about using an indicator method, and go back to our curve, if we have something that changes color at a certain pH, and let's say it changes color up here at 9, and it's going to be a different color from this higher point and up. I have no idea in the lower part of the region, until I get to the point of color change, I have no idea where I am in the progression of this titration. Okay, but a pH meter helps us monitor that. So if we have a pH meter, no reason not to use it, but if we don't have it, we use these color changes. So if we look at color changes, we're taking and doing our titration, and we have this indicator added to the solution that's going to change color at some certain pH. Alternatively, we can put our probe in there and we can monitor it with the pH meter. So the one that we're going to use in lab next week is an indicator called phenolphthalein, and phenolphthalein changes color, starts changing color about pH 8. Okay, at pH below 8, it's colorless. But then at about pH 8.5, it turns a light pink, and as soon as you get to pH 9, it's this dark pink. And what we would like to do is we would like to stop the titration when we get to light pink. This is our stopping point. That's what we call the end point. And the reason we want to stop it there is because once it turns to the dark pink, it's the same dark pink from there on. And you don't know how far you've went. So we choose this intermediate color. And if we look at the structure that changes phenolphthalein in acidic conditions and neutral conditions, it's colorless. It undergoes a molecular rearrangement at higher pH. It has a double ionization event that occurs. It loses 2 hydroxides off. And when that occurs, this is the color change that we'll see. This is where we're trying to stop. Stop here. That's our goal. If we get to this color, you don't know if it's pH 10 or pH 13. It's too far. So we want to stop it at this intermediate in the course of the titration. So indicators are simply acids or bases themselves that undergo some type of rearrangement as a function of pH. And whenever they change, what happens is they change color. So with the ionization event, there is a color change that will occur. So it's a color 1 versus color 2 situation after the ionization event. And with the case of phenolphthalein, it may go from colorless to having color. Sometimes it just changes from one color to another color. There are a lot of different types of indicators that occur. But if we think of this being an ionization event, this is going to be described by a Ka. So one way that we can look at this is where it's going to occur is look at the pKa of that indicator. So if the color is within 1 unit of the pKa, okay, it's going to be a factor of 10 of the color 1. If pH is 1 unit below pKa, it's going to be a 10-fold excess of color 1, and that's the primary color you're going to see. Like we just saw, if pH is equal to pKa, that's going to be where the intermediate is because it's a mix of the two colors. And then if pH is 1 unit above it, you're going to see primarily color 2 in the system. So it's always a mix of colors, but the amount of those two colors is depending on where pH is with relationship to the pKa. So here's another one that changes colors. This is an indicator called methyl red. It goes from a pink at pH 2 and 4. At 5, it's an orange color. And then at 7 and above, it's a yellow color. Now, it's a lot easier to see colorless to having color. We do a lot of these types of titrations in the chemical analysis course. And about every third year, I find a student that is doing a titration. And there's one that we see where we go from a blue to yellow. And if you go from blue to yellow, if you mix blue and yellow, what color you get? You get green. And I have a student that doesn't see the green intermediate. So we're supposed to stop it when we see green. And they go through the whole volume of the burette, and they say, this thing's never changed. What are you talking about? And we find out that person's colorblind. A lot of people are colorblind, and you don't know it. Because we observe the world, and it just seems like it is. We don't know that there are shades that we don't see. If that's the case, if we have that physical limitation, we just choose a different indicator. That's not a problem. But I'm shocked at the fact that, and I typically have a class of 15 to 20 in that. So 1 out of every 60 students has that difference in the way that they view the world that the rest of us don't, and they don't know it. Okay, and we have the same thing with our senses of smell, senses of taste, and senses of hearing. We're all unique and see things differently. This is just one I see because of this particular application of looking for that. We're looking for this particular intermediate to know when something's happened. And some people just can't see it. Okay? Maybe orange is the thing you can't see. And what happens if you don't see orange color here, okay, if 5 doesn't look different, you'll see it as either being like one of the other colors above it or below it. So it's not that it doesn't exist in the spectra, it goes black or gray, you just see it as one of the other colors. And you don't know it's not there. That's a unique thing about the way color is. And it's also the reason art is very subjective. The same way that we sense colors with our eyes, the photoreceptors in our eyes, the way our brain does the neurochemistry, and everybody looks at a painting and their favorite color pops to them. And everybody's favorite color is slightly different. So you look at a piece of art and you love it because that sensation in your brain fires. I look at that same piece of art and I'm going, that's not something I put on my wall. Everybody sees things differently. Okay? All right. So we can follow the course of titrations with indicators, and we can look at where the big jumps occur in pH. That's going to happen when a very small amount of titrant's added, typically near the equivalence point, and you're talking about less than 1/10 of a mil. So how many drops are in a milliliter? So if you take an eyedropper and drop it, does anybody remember that or ever had to count that out? If you just do drops of water, there are about 20 drops per milliliter. So every drop is 5/100ths of a mil. This color change is going to occur from one extreme to the other in 2 drops maximum. A lot of times it's going to occur in 1 drop. Okay? So when we're adding these volumes, we have to control it down to the drop to get good data out of it. So this is where we have to be use of self-control and slow things down. You're trying to get out there quick, but if you go too quick, let the volume, you'll add 1/4 of a mil in there, and all of a sudden your color change is gone. I mean, you're already at the far extreme of the color change, and you have to start over again. So we can use this by matching the pKa of the indicator to the pH where it's going to be at the equivalence point. We can choose the right indicator to match that particular titration. So if I'm doing one with an acid, strong base, I want something that changes right after setup. If I'm doing a weak acid and a strong base, it forms the conjugate base at the equivalence point. That equivalence point is going to be higher than 7. So if you're doing acetic acid, it's pH 8.6. So I want an indicator that's going to change pretty close to 8.6. If you're doing something that's even a weaker base, so if you're titrating something like, or a weaker acid like ammonium chloride, that pH change is going to occur all the way up at pH 10. Okay, so now I have to have an indicator that starts to change about 10.5. You have to match the indicator with the titration that you're doing. So that requires some foreknowledge, and the other thing requires is, do you have a physical limitation? Can you see the color change that's going to occur? Here's the common one that we do. Bromo Creosote green. We go from at acidic pH, it's yellow, to a little bit higher pH, it's blue, and we try to stop it at this green intermediate, and some people can't see that. Okay? There's a lot of different choices. So if that one doesn't work, let's choose one that goes from red to orange. But the best ones to use are the ones that go from colorless to having color. All right, and here are a couple that go from colorless to red, colorless to pink, colorless to blue. Those are the ones that are easiest to see the transition. Okay, we're going to work some problems with calculations at the end of the chapter. I want to go ahead and cover what's left in the notes. The last topic in chapter 17 is looking at solubility equilibrium. So we want to know if an ionic compound is going to dissolve or not. So we've been classifying ionic compounds. So that's a mixture of a metal and a non-metal. Okay, for ionic compounds are metal and a polyatomic ion. And we've said the generic classification is soluble or it's insoluble. Okay, but in reality, there is a very small amount of that species that dissolves every time. So now we want to start looking at the things that we've classified as insoluble and find out how far that equilibrium went in the forward direction. So what is the extent of the solubility? So when I say that, if we look at something like, we'll do this one problem in a minute. Silver chloride is a classic thing for solubility. Silver chloride is classified as insoluble in water. But the reality is that these things dissolve in water at about in the neighborhood of 10 to the minus fifth, 10 to the minus sixth molar. Not very much at all, but there's a little bit goes into solution. Okay, and we want to find out exactly how much goes into solution. So the equilibrium that describes that is called the solubility product, or the KSP. And if we look at this dissociation of the salt that I just gave you, throw that back over here, fix my arrow. I don't know why it off shifts all these today. If I look at the solubility of silver chloride to produce the silver and the chloride, cation and anion, and I write the equilibrium constant expression, which we call the solubility products, it's products over reactants. So the products are the silver cation and the chlorine anion. Why isn't the silver chloride parent compound, why doesn't it show up in the expression? It's a solid. That's exactly right. Because it's a solid, it doesn't appear. Recognizing this as a solid means that it doesn't appear in the expression down here. So the things that are going to be in the KSP expressions are just the things on the right-hand side of the equilibrium. On the left-hand side, it's the solid. The things on the left that dissolve in solution, those are the things that are going to be in the KSP expressions. All right, so I told you they vary a lot. Well, they vary to a great extent. Here's an example of some of the common salts. And you'll either get this table, I'll have to figure out what I'm going to put on the test when I write it. I'll either have to give you the KSP values in the problem or a copy of the table. Okay, one or the other. I think in the past, just to save paper, I've given the specific KSPs with each particular problem. But they vary for things that are somewhat soluble. Something like barium fluoride is 10 to the minus fifth. All right, calcium sulfate is 10 to the minus fifth. Lead chloride is 10 to the minus fifth. And you look at things that are not very soluble at all. So silver iodide is 10 to the minus 17th. copper sulfide, 10 to the minus 36. Okay? That means that the arrow doesn't go forward very much at all if it's 10 to the minus 36. It heavily favors the products. So this compound's not going to dissolve very much at all. But if I have an equilibria that involves copper, I need to know what is the concentration of copper. I can figure out how much that would be in the system. Okay, so thing is they vary considerably from slightly soluble compounds to very, very insoluble columns. The solubility of something is defined as how much of the solute dissolves in a given amount of solution at a particular temperature. All right, so whatever that temperature is, we typically set it at 25, but we talked about solubility rules earlier. As temperature goes up, typically solubility goes up. And if temperature goes down, the solubility of things go down. In organic, the way that we supersaturate solutions, we talk about this, is you heat the solvent up. And you get it all to dissolve. And then you cool the solvent down. And we can create a crystal and precipitate that crystal out like that. So when we talk about the term molar solubility, it's simply the moles of a particular solute, the compound we're interested in, that dissolve in a liter of solution, or the molarity of that particular species. Okay? Now, if we look at our generic salt, metal salt that's going to dissolve, M represents the metal to the power of its charge. Little n represents the stoichiometry. The little m is the stoichiometry for the nonmetal to its power. And the generic expression we have that calculates the molar solubility is the square root, or the root of KSP divided by n to the n power times m to the m power, where these represent the stoichiometry numbers. And then you take the summation of n plus m root of that. Okay, I know that's, what the heck did you just say? I'm going to show you one in a second. So here's a table that puts this to work for different things. So if it's a 1-in-1, so if it's something like silver chloride, so I'm going to go in and put a blank page in here and show you silver chloride. So if silver chloride, we've already said it dissolves to produce the silver and the chloride. Right, so this would be a 1 and a 1 in the stoichiometries. So the KSP expression would be the concentration of the silver times the concentration of the chloride. And if we want to think of monitoring this solubility, how much of this goes forwards? If this is S, this is 1-to-1, this would be S, and this would be S. So KSP would be equal to S squared. That means that the solubility would be the square root of KSP. So if I want to apply it to this equation, I'll come back to this page in just a second. So if I'm going to apply it to this, right, so it would be the solubility, molar solubility, is equal to the root of the 1 plus 1, so that's square root, 1 plus 1, KSP divided by 1 to the 1 power times 1 to the 1 power. So that simplifies to just KSP, square root of KSP. So if it's a 1-to-1 salt, that's our formula. The solubility is the square root of KSP. All right, and it doesn't matter if that salt is singly charged or doubly charged, as long as the mole ratio is 1-to-1. So like in silver chloride, it's S and S. In barium sulfate, plus 2 minus 2, it's still S to S, and it's the exact same formula. But if I change the mole ratio, it changes. So the next one's silver carbonate. So if I go down and look at silver carbonate, so what happens with silver carbonate? So silver carbonate dissociates at a different ratio. There are 2 silvers to 1 carbonate, So if I want to think of solubility, it would be 2 times the solubility and then solubility. KSP would be the concentration of the silver squared times the concentration of the carbonate. But if I'm going to substitute these S's in it, it would be 2S for silver, so 2S squared, and S for the carbonate. If I square 2S, it's 4S squared. So it's going to become 4S squared times S, 4S cubed. So KSP is equal to 4S cubed. Right? So if I want to apply that to solving for the solubility, it's the cube root of KSP divided by 4. Now applying that back to this equation from the previous page, it would be the root of 2 plus 1, so that would be 3, of KSP divided by 2 to the 2 power times 1 to the 1 power. So on the bottom, that's the 4. It's the same thing. Okay, so here's where you kind of have a choice on how you're going to deal with these. And I'll answer questions. You've got a choice of, I'm giving you this on the equation sheet. Hopefully you've already looked at it. You have to understand how to apply the N's and the M's, or some students choose just to memorize the shortcuts. And there's not that many, because if I look at these, there are just a couple of possibilities we're going to run into. If they're 1 to 1, this is my formula. If it's 2 to 1, the one we just did, KSP is equal to 4 times, KSP equals 4 times the solubility cubed. Okay? That works for the 2 being on either species. 2 on the cation or 2 on the anion, as long as it's a 1 to 2 ratio. If it's a 1 to 3, if you plug it in, KSP is equal to 27 times the solubility to the 4th power. Our solubility is equal to the 4th root of KSP divided by 27. Now, I told you a while back you'd need to be able to take a nth root in your calculator. This is why. Right? So make sure in your calculator you can do a 3rd root, a 4th root. Okay, so on some of your calculators, you've got a button and you can put, you've got a Y to the X button. Okay, so Y to the X button on your calculator, and you can just take something to the 1 divided by 3. That's equivalent to the 1/3 power. Right? Some it has a button that looks like this, and that'll let you take to the nth root, 4th, 5th. You got to figure out what your calculator has. So as I start doing a few of these problems, you figure out what you've got in your systems and you can do. All right, let's look at a couple of these. So your choice. You're either going to memorize the things in this table, and here's the last one. If it's a 3 to 2 ratio, its KSP equals 108 times the solubility to the 5th. So you've got things, choices 1, 2, 3. There's 4 possibilities in this table that you can memorize these things, or you can learn how to use that equation. Okay. The thing I'll tell you is that if you continue in chemistry, you're not going to, everything's not going to fit these. If this will fit 80% of what you run into. But then you're going to run into things that don't fit in these combinations. And then you have to be able to use that equation. So you choose your approach to how you're going to do this test. Okay, so let's do a couple of examples. What's the molar solubility of silver bromide? So, and this may be different than the problem you have on your page because I changed it. So I've got the KSP given to me, and I want to know what's the solubility. The key thing to recognize on this one is it's a 1-to-1 salt, and because it's a 1-to-1 salt, this is S, 1-to-1, So KSP is equal to S squared. That means that the solubility is equal to the square root of KSP. It's a simple matter of plugging that number in. Solubility is equal to the square root, plug in the number for KSP, and it's going to represent the molar concentration. So I get 7.31 times 10 to the minus 7th molar. So that's how much silver bromide goes into solution. All right, question on that one. Okay, let's do the other one right quick. So this one, solubility, and this is a 1-to-1, so that's going to be S. This is going to be 2S. If I look at the KSP equilibria, the KSP expression is the concentration of the lead times the concentration of the chloride squared because of the 2. Now if I plug the S's in, it would be S times 2S squared. So this is the one that is 4S cubed. So then if I want to solve that, solubility is equal to the cube root of KSP divided by 4. All right, so lead chloride is quite a bit more soluble than silver bromide. 1.17 minus 4. And I got 1.43 times 10 to the minus 2 more. So if I just compare those two salts, there's 5 orders of magnitude difference between the two in solubility. That's a bunch. Make sure you and your calculator are happy enough with each other. You can get that answer right there.
Wait, I didn't get.
Okay.
You said this button right here.
That's your Y to the X button. Okay, so if you're going to do that, you're going to put in, take this divided by 4, get that, and then you're going to raise it. So this KSP divided by 4, and on your calculator, you're going to have to raise it to the 1/3 power. So you're going to have to take the inverse of 3, and that's what you're going to put into the Y to the X button.
Okay, I got it.
Okay, so yours has got that button. Mine actually has the this old school timey guy didn't figure we could figure that out, so it's got a mine's got this button, so it'll do the nth root directly.
1 second. Yeah.
Okay, good. All right, anybody else got a question there? All right. So if we look at things about the KSP, the magnitude of the KSP tells us something about the relative solubilities of these compounds. You can't always just look at the KSP values by themselves, because if they don't dissociate at the same stoichiometry, you're taking them to different roots. So if everything is a 1-to-1, then you can look at the one that has the largest KSP and it's going to be the most soluble. And the one with the lowest KSP is the least soluble. But that's only true for things that have the same dissociation stoichiometry. So like in the example problems here, these are old exam questions. So if I gave you this series of salts, they all dissociate into 1-to-1 stoichiometry. And that's the trick to answering this problem. They're all 1-to-1. So one that's got the smallest or the lowest molar solubility is going to be the smallest value for KSP. So I've got 10 to the minus 13th, 10 to the minus 28th, that's pretty small. 10 to the minus 16th, but 10 to the minus 29th is the smallest, and that's the reason cadmium sulfide is the least soluble. Okay? Now the problem below is trickier, because here I ask you which one has the lowest molar solubility, and I give you a list of solids to choose from. But the thing that's different about this one is they don't all dissociate in the same stoichiometry. So this one is 1-to-1. This one's 1-to-1. But this one is a 1-to-2. This one's 1-to-1. So if I look at just the values, the one that's least soluble looks like it's probably, here I'm looking for the smallest. This one's 10 to the minus 29. 1-to-1, 10 to the minus 13th. And this one, it's 10 to the minus 16th. So of the ones that I have, this it looks like the winner. But if I look at the one where I'm going to have to take the cube root of it, when I take the cube root of it, so if it were KSP divided by 4 and take the cube root of it, it's even going to be more soluble. So this is definitely the one that's the least soluble in this. So this guy is going to be like 10 to the minus 5th solubility if I plug in the value. It's approximately 10 to the minus 5th, 10 to the minus 6th. Just make sure you're comparing apples to apples. Okay? If something's not the same stoichiometry, you have to do some type of crude calculation to figure out what's going on with it. Okay, here's a simple one. Do this one. Okay, just lost one. One more. Okay, we're all in. Most of you says choice B. So the key to this problem is recognizing what the dissociation stoichiometry is, as all of these problems are. Silver's a +1 cation, chlorine's a -1. S, S, and S. It's a 1-to-1. If it's a 1-to-1 salt, solubility is the square root of KSP. You take the solubility of the square root of that guy, you indeed get choice B, which most of you put. Okay. Question on that? All right. Now the next thing we want to look at is what we call the common ion effect. And it's an application of how Le Charpier's principle comes into play with the solubility equilibria. So what happens if I add the addition of one of the ions that's involved in the solubility equilibria, either the anion or the cation, it decreases how soluble the salt is. If you look at the example of calcium fluoride, dissociates into the calcium and the fluoride ion. If I were to throw some sodium fluoride in here, that means that sodium fluoride is freely soluble. The concentration of the fluoride ion is going to increase, and Le Charpier's principle tells us if we increase the amount of a product, how does the equilibrium respond? Just back to the left. So that means as this shifts back to the left, it decreases the solubility of the co-ion. All right, so the solubility of the calcium fluoride is going to decrease in this case. So we just want to be able to predict how that occurs, and we can actually apply it to a problem. So if I look at what is the molar solubility of silver bromide, first in pure water, and then we're going to look at it by adding just 0.001 molar of the co-ion from sodium bromide. So just in pure water, it's a 1-to-1 salt, and it's simple to do as a 1-to-1. So solubility and solubility of 1-to-1 KSP is equal to S squared, so S is equal to square root of KSP. Solubility is 8.8 times 10 to the minus 7th. Okay, so that's a straightforward, simple one, just like the one that we just did with silver bromide. But now if I have this bromide ion added, it's only there at 1 times 10 to the minus 3rd molar, 1 millimolar. Now what I have when I write the KSP expression, KSP is equal to the concentration of the silver times the concentration of the bromide. But I've got bromide from this solubility, and I've got bromide from this source of the co-ion. Now, from just the solubility itself, it was 1 times 10 to the minus 7th. Here's 10 to the minus 3rd. So the total bromide is equivalent to the bromide that's coming from it's sodium bromide, not potassium, from the sodium bromide. The way this simplifies things is this is S, this is known value, it's 0.001. So now KSP simply equals to 0.001 times S. You divide the 0.001 over, and the solubility is 7.7 times 10 to the minus 10th. Okay, so just the simple addition of this salt being present at 1 times 10 to the minus 3rd molar changed this from 10 to the minus 10th, where it was 10 to the minus 7th. It changed it 1,000 times, or 3 orders of magnitude. That's the reason we have to be aware that these co-ions being present can greatly influence the solubility. And when you look at the salt concentrations inside of cells, the salt concentrations in cells range from somewhere in the range of 0.1 to 0.25 molar. They're much, much higher than this. So salt concentrations that exist inside of cells and living tissues have a great influence on the solubility of compounds where the co-ion is present. All right? If the co-ion is not part of those salts, then it doesn't influence the equilibrium. All right, so let's do another example of this. If you have something that associates into a species that is influenced by pH, like a weak acid or a weak base, or a conjugate acid or conjugate base, they are influenced by pH. So if we look at hydroxides are common things, when something like magnesium hydroxide dissolves into water, it produces the magnesium and the hydroxide anion. So what happens if the pH goes higher of a solution? So increase in pH means that the concentration of the OH minus goes up. So if this concentration goes up, Le Chartier's principle says this thing's going to decrease in solubility. Now the converse of that's true. If I take into decrease pH instead of increasing it, that means that the concentration of the OH minus is going to go down. And if this concentration were to go down, that means it's going to shift in the forward direction. So the lower the pH, the higher the solubility for these hydroxide compounds. The same thing works if we look at conjugates of weak acids. So something like calcium carbonate in limestone, it's not very soluble. If I take a piece of chalk and throw it in water, it doesn't dissolve. But if I take and add some acid to that solution, the acid will react with the carbonate ion and convert it into the bicarbonate. So as I do that, the concentration of the carbonate goes down. So this goes down, the equilibrium shifts by going forward. It was one of the first labs we did in Gen Chem 1. We did the separation of silicates and calcium carbonate in limestone, and we added acid to limestone, and the calcium carbonate dissolved and formed bubbles, and then we were left with the silicon dioxide that's left. So what happens is that low pH, these compounds like carbonates have a higher solubility. So anytime that you have a base present, if you take the pH down, you're taking that base and you're protonating it, and you're decreasing the concentration of the deprotonated form. And it's going to become more soluble in a system. All right, so thinking about what I've just told you about the common ion effect, I want you to tell me which one of these systems would be influenced or would influence the solubility of this compound, lead chloride. And I'll let y'all talk about this one. So this is a group problem. Okay? So you've got 4 choices. Which one of those has something to do with the solubility of lead chloride? Now, on the old software, I loved my clock because there was a countdown timer. You got nervous watching it. So, all right, get an answer in.
Yeah.
I know, there's one.
But I can see where it can be seen. Just
Okay, take a blind guess in the dark then. All right, we're in. Okay, came down to 2. Everybody said it was a choice B or D. So the way you address a problem like this is you look at the compound whose solubility is of concern, and you look, is there anything that can alter either one of these ions? So would they be changed by pH, or would they be a co-ion in something? So iron nitrate, if it dissociates, it produces iron 2+ and the nitrite ion. Neither one of those has significant pH effect, and neither is a co-ion in this. So A is out. Sodium fluoride dissociates into the sodium and the fluoride. Neither one of those is a co-ion. Okay, so this is actually a weak base, but neither of these are affected by pH, so the base doesn't have an influence. These out. The one that I've got chlorine from the solubility of potassium bromide or potassium chloride, and I've got chlorine here. So if I throw some potassium chloride in there, it increases the chlorine concentration. Common ion effect decreases the solubility of that particular compound. So, see. Okay, you're looking for the common ion. Right? That's the way we approach these types of problems. Okay. So, how do we predict if something's soluble or not? Given the certain concentrations of ions, is something going to be soluble or not? Is what we're going to do is look at the solubility, and we're going to take the concentrations that are given, and we're going to calculate a Q. And a Q is much like we talked about Q earlier, in predicting if equilibriums are going to proceed in the forward direction or reverse direction. Here it tells us the state of the saturation in the solution. If Q is equal to KSP, that means the solution is saturated at that point, but it's not going to form a precipitate. If Q is less than K, it means the solution is unsaturated and there's not going to be a precipitate form. If Q is greater than K, that means that the solution is saturated and that a salt or a precipitate will form in the solution. Okay, so we talked about what supersaturation is already. Sometimes we can trick it by heating a solution up, and it's not going to form a precipitate unless it's disturbed. But the way that we calculate Q is simply the same way that we calculate KSP. It's the concentration of the metal raised to whatever that power is times the concentration of the nonmetal raised to whatever its power is. Okay? All right, here's just a couple of examples. Here's potassium chromate and silver nitrate added together. When the two things are added together, the equilibria forms silver chromate. It's two silvers with one chromate molecule. And the fact that we see the solid present tells me that the Q is greater than KSP, and there's going to be a precipitation occurs. And then when we can do things tricking it like the sodium acetate, you can take a solution of sodium acetate, heat it up, and add a lot of sodium acetate to it, get it super saturated, let it slowly cool, and then you can drop a seed crystal in. As that seed crystal falls and hits the solution, the crystallization process spreads out very rapidly, so that crystal hits, and in a matter of seconds, it's snowballed, and you got this huge crystal inside of the solution. We looked at an example of those. Okay, so every chapter has to have something that's the fun part. This is not it, okay? Qualitative analysis is a scheme where we can do selective precipitations to identify what something is, and it's a classical wet chemistry technique. And what it is we can take a solid compound that's slightly soluble, and we can apply several different precipitating agents, and from that we can follow what's soluble and what's not to try to identify something. It goes something like this. You have a mixture of cations in a solution, possibly A, B, or C. The first precipitating agents are added and it reacts with cation A, so you see if A falls out of solution. So A is either there or not. So you pour the liquid off and you've got B and C cations potentially left. You add a second reagent, it reacts with cation B, it forms a precipitant. So now you would know B was present, you pour that off, and you're left with the possibility of A. It would be nice if it were that simple, but it's not. Oh, my page is missing. No. Okay, we're getting that. I'm going to open up my last year's notes. I know that page is here. And the thing I'll tell you about this where it's loading is that I don't expect you to memorize these. Shoot. It's on this one. These are, there's a lot of steps of possibilities. They go back to the solubility tables that we talked about. Older notes. Have that. You can look at that figure in your textbook. It's a flow chart looking thing where it goes through. You add this to it, it's this, if it precipitates. And this, it's this one. And I don't have my textbook with me to tell you which table that is. It's the last table in chapter 17. It's the one full of color because there's about 30 different arrows that go on with it. All right? Okay, so I'm going to let y'all do a little quick vote here. Do you want to work a few problems at the end of the chapter, or you want to call it quits today and do them all tomorrow?
Let's go tomorrow.
Tomorrow? Okay, so we'll spend the whole day tomorrow. We'll spend most of it. I'll at least give you 10 or 15 minutes at the end to ask questions or test review. But we'll spend tomorrow working all the problems at the end of the chapter.